Okay, so you recall that the answer for dy by dx here was e to the 3x into 3x plus 1. That's going to form the first part of our proof by induction. Okay, so proof by induction, we don't need to write anything too fancy down here. People put, P of n, let P of n be the statement such that, okay, you can do that notation, it's fine. But we're going to get straight to it. So we're going to test for n equals 1. So testing for n equals 1. Now, we really want to have a little look at the left-hand side and right-hand side here. Some people made mistakes by not considering these two sides fully. So the left-hand side of this statement is d1 of y by dx of 1. Now, we've actually got that answer from part A. But we've got to make that explicit that the left-hand side becomes the first derivative, which is e to the 3x into 3x plus 1. And now the right-hand side is clearly given by this expression here. And so when n equals 1, the right-hand side is 1 into 3 of 1 minus 1. My advice here is always write it out, no matter how trivial it might seem, no matter how easy it'll be to do in your head. But you have to have this structure, this setting out here. So this is 3 to the 0, which is 1. This is like e to the 3x here, plus 3x e to the 3x, which clearly is exactly the same expression as the left-hand side, which we got from part A. And so this is true for n equals 1. Okay, so that's really important that you actually compare left-hand side and right-hand side for that. Okay, now the second step, so this is the first stage of proof by induction always, yeah? The second stage, now the language is incredibly important, yeah? Something that is incorrect is this, n equals k. Well, yeah, we're doing something with n equals k, but we're actually doing something a lot more than just n equals k. We're actually going to write down, we're going to assume that the statement is true, yeah, for n equals k. So the statement is true for n equals k. And then go and write out the statement. That's dk of y by dx of k. The kth derivative is equal to k3 to the k minus 1 into e to the 3x plus x into 3k e to the 3x. Okay, so that's the second one. Assume true for n equals k and then write the statement marks for that. And then the third part, and we'll carry on the next page, is consider the next case, and that's n equals k plus 1. Yeah. So that's the structure of it. The next part now is quite a crucial part. We want the k plus 1th derivative. Okay, so we need to consider the left-hand side, which is d, the k plus 1th derivative of y with respect to the k plus 1th of x. And we get that by simply differentiating with respect to x the previous derivative, which is the kth derivative, which is what we have under here, dx to the k. Yeah. So essentially we're taking this expression, which we're going to assume to be true. If this expression is true, it would mean that when we differentiate this, we'll get the k plus 1th derivative, and we should be able to manipulate this so that it looks like just the same as this, with a k plus 1 substituted in place of the n. So that's the challenge. Okay, so this is the last part of the proof by induction. So we've got the kth derivative is here, that's what we assume to be true, and we're going to consider the k plus 1th case. Okay, so we realise that the k plus 1th derivative we get that by differentiating the kth derivative. So it's just the next one down. Okay, and this is where the inductive step comes in, because we're going to use the part that we assume to be true, and we're going to work on it and try and manipulate it so it's in a form, just the same form, but with the k replaced by the k plus 1. So that's equivalent to d by dx of all of this guy coming into here. So I'm going to write it out, k e to the k minus 1, 3 to the x plus 3 to the k e to the 3x times by x. And a little mistake there, k e to the, that's 3 there. That's a bit silly, 3, and that's e to the, how did I get all that wrong? E to the 3x, that was rubbish. Okay, so let's differentiate this. So this first part, there's a lot of constants here, there's an e to the 3x. So this will be 3k, 3 to the k minus 1, and that'll be an e to the 3x. That's that sorted out. This one here, we've got to be careful because I've got a variable here and a variable here, so it's going to be a product rule again. So I'll factor out the 3 to the k, and then I'll just do this with a product rule. It's e to the 3x times by 1, plus leave the x, e to the 3x times by 3. So that's similar to what we had before. Okay, so we could be playing around with this algebra for quite some time, but we need to know what the end goal is. And I think the end goal, if we write it up here, was to have this thing here. So this is n 3 to the n minus 1. So if n is k plus 1, we'll have k plus 1 is what we're aiming for. 3 to the k plus 1 minus 1, so that's 3 to the k. That'll be e to the 3x plus x, 3 to the k plus 1, e to the 3x. So that's what we're heading towards. So we're just got to try and manipulate it to get to that particular stage as we see it. So let's just keep going. 3k, 3 to the k minus 1. The 3 will combine with the 3 to the k minus 1 here. So that'll be great, because that'll be just k times by 3 to the k, and then e to the 3x. And then let's just expand this. This is 3 to the k, e to the 3x, plus 3 to the k times by 3 is 3 to the k plus 1, times by x times by e to the 3x. And I think we've got the format we need now. We want 3 to the k, e to the 3x, 3 to the k, e to the 3x here, 3 to the k, e to the 3x here, k lots plus 1 lot. So that's the k plus 1. And then that's e to the 3x times by k plus x, 3 to the k plus 1, and then e to the 3x. So we've manipulated it into the form we need. So there's only one mark left, one stage left, and that's the actual language you use to put it all together. And there's always 1 mark given for this, and on the mark scheme it's called R1, 1 mark for your reasoning. The reasoning always follows the same structure, the same method, and you should really just match it. If we assume true for n equals k, this implies that it's true for n equals k plus 1. So if the statement is true for any arbitrary value k, where k is an integer, then it's definitely true for the next case. Okay, so you just have to prove it's true for a single numerical case, and then everything else, falls into place. So you have to write down the statement that you found that it is true and verified it's true for a particular case, and you proved it was true for n equals 1. So therefore, if it's true for n equals 1, it's true for n equals 2. If it's true for n equals 2, it's true for n equals 3, etc. Therefore, true for all n. Now, there's different symbols you can use in here, but the language is the most important thing. The language shouldn't be very much different from that.